Hello, this is Professor Keen. This is the third of my lectures on Chapter 16 of A Student's Guide to the Great Physics texts. This is on Pascal's treatise on the equilibrium of fluids. In this lecture, what I want to talk about, this is again Pascal's treatise on fluids. This is from A Student's Guide, Chapter 16. This is the main point that I want to talk about in this lecture, is that all of the effects that had previously been attributed to the idea that nature abhors a vacuum, Pascal claims, are better attributed to the weight of air. So all of the effects previously, all the effects previously attributed to nature's abhorrence of a vacuum, that was nature hates a vacuum, right? Nature abhors a vacuum, are better explained or better attributed to the fact that air has weight, or the weight of air, and specifically the weight of our atmosphere. This is the main point that Pascal was describing in this chapter and that we will be drawing out in the next few minutes. Okay, so the first thing that he talks about, he numbers things, so they're pretty nice to talk about. He talks about this. He says, well, remember when we had been discussing a long tube submerged in, let me move this over to here. Remember when we were talking about a long 20-foot long tube that has a bellows attached to the bottom of it? So we've got a bellows right here, and this right here was water, and out here there is air, and there's air inside of this. And remember the idea that the water was pushing on the sides of this bellows, again due to hydrostatic pressure. So the bellows is hard to open. So the bellows is hard to expand. Of course, you could puncture a little hole in the side of it, and if you did that, the water would rush in, it would fill up the bellows, and then it would be easy to open and close because you have the same weight of water inside pushing out as the weight of water pushing in. But insofar as this is just air in here going all the way up to the top, there's no weight of water inside of it pushing out, and so the weight of the water on the outside pushing in is really hard to overcome. So why is this relevant to what we're talking about here and now? Well, the idea is that you can consider a bellows as well, a very long bellows tube, but this time, instead of the bellows being submerged underwater, you can imagine that the bellows is submerged under an ocean of air. Okay, so here is air, and out here is the vacuum of space, and here is the ground. So this would, of course, have to be a very, very long tube, many miles long, but the idea is if you could do this, so there's vacuum out here, so there'd be vacuum inside of the tube, and there's air, well, that air is pushing on the outside of the bellows with a force that is dictated by how tall how tall this atmosphere of air is. And similarly, just like in this case, the bellows is hard to expand. It's difficult to expand because the air is pushing on it. And here is the interesting, so that's insightful in and of itself, but let's draw this conclusion one step further. Let's take this bellows, and instead of having this tube going all the way out into outer space, we would just take this bellows and just cap it off right here. So this is sealed, and it's under this atmosphere of air. And out here in outer space, once again, there's a vacuum right here, and this is the ground of the Earth. And here, once again, the air is pushing in on it right here. And in this case, instead of having a bellows with a tube going out to the vacuum of space, we just have a bellows with vacuum inside of it like this, and it's sealed. And we would say that the sealed bellows is hard to open. And the reason it's hard to open is not because in order to open it we would need to create a vacuum in it, and that's hard to do because nature abhors a vacuum. Rather, it is because the air is pressing on the outside. After all, in this case there's a vacuum inside of it, and in this case there's a vacuum inside of it. It's hard to open here because of the weight of air. It's hard to open here because of the weight of the air. So the exact same explanation that allowed us to understand why it is hard to open a bellows underwater is the explanation that allows us to understand why it is hard to open up a sealed bellows that's in our atmosphere. If, of course, we were to take this to outer space, it would be very easy to open and close it. But because of the weight of air, it is difficult to open it. Okay, let's go on to point number 2. I'll probably get through 2 or 3 of these today, and maybe go on to a couple of them in the next lecture. Pascal explains how the weight of air is precisely what makes it hard for us to lift up a polished glass microscope slide. He doesn't use a microscope slide, he just says a polished glass surface from another polished glass surface. Well, why is that? Well, because we have this atmosphere, we have air up here, and the weight of the air is pushing down on this microscope slide. And so the glass slide is hard to lift. Why is it hard to lift? It's hard to lift from a polished surface due to the weight of the air. What's critical here is that it's polished so the air does not get underneath it and push up from the bottom. You have only the air pushing down from the top, right? If, on the other hand, let me expand this, we were to take, instead of a polished piece of glass, a rough piece of glass, I'm going to exaggerate the roughness here to make my point, this rough piece of glass sitting on this table, again under this atmosphere, this air. Well, the air now is once again pushing down on the top of it, but because it's rough, the air can slide underneath it and push up on the bottom of it as well. And so there's not this differential pressure across it here. Here there's a pressure from the top but no pressure due to air from the bottom. Here you've got air pressure from the top and air pressure from the bottom. And so in this case, the glass slide is easy to lift. Because the air is beneath it as well. And pushes upward, pushes both down and up. Of course, if we were to be nitpicky about this, the air pressure at this point, at this height, is a little bit the pressure on the top of it is a little bit bigger than the pressure on the bottom of it. I'm sorry, I said that in the reverse. The pressure on the top is a little bit less than the pressure on the bottom. So there's a slight buoyant force that's lifting it up, but the buoyant force is very tiny anyhow. What's really the reason it's hard to lift this up is just because of the weight of the glass, and which isn't very much anyhow. So the air pressure doesn't really have an effect on this.